What triangle comes from a socialist country? An equilateral triangle. Equal, everything shared. And then what dances do the twin isosceles triangles excel at? Well, you put them together, it's the rhombus. Anyways, we will be talking about isosceles and equilateral triangles today. So you've already heard of isosceles triangles back in 6th grade. And now you're going to learn a few more of the formal words for isosceles triangles. First of all, the congruent sides are called the legs. So I've labeled the legs, and I'd recommend you do the same on your drawing. The vertex angle is formed by the two legs. So it's usually the odd man out, the angle that doesn't match the other two. The side opposite the vertex angle is the base. And the base angles are the two matching or congruent angles that share the base as a side. Now, the main isosceles triangle theorem says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So if I highlight that, you see this side goes with this angle, and this side goes with that angle. If the two sides are congruent, then those two angles are congruent. Now, you can also go the other way. You can start with the angles going with the sides. So if the two angles are congruent, then the two sides opposite those are congruent as well. So we're going to find y in triangle LMN. I don't have any angles marked, but you can see that two sides are congruent, so we can assume that this is an isosceles triangle. If it's an isosceles triangle, then that means the two base angles are congruent. So I went ahead and marked them congruent, and I put a y down here since they're both equal in measure. Then I can use the triangle sum theorem, which says that each of the angles, when you add them, equals 180. So y plus 34 is 180. Combine like terms, 2y plus 34 equals 180. Use the subtraction property of equality. I subtract 34 from both sides, and I get 2y equals 146. Divide by 2, which is the division property of equality, and I get y equals 73. So the main point here was knowing that the two base angles were congruent, and so if one base angle is y, the other base angle is y, and then just use the triangle sum theorem to solve. Now, there are also some equilateral triangle corollaries. If a triangle is equilateral, that means if all the sides are congruent, then it is also equiangular. All the angles are congruent. And vice versa. The converse is, if a triangle is equiangular, all angles congruent, then it is equilateral, all sides congruent. So here we have an equilateral triangle. You can see because I have all the sides marked congruent. Well, if it's equilateral, then it's also equiangular. So I can say that all the angles are congruent, and since there are only 3 angles in a triangle, these must be 60 degrees. That tells me that this right here has to equal 60 degrees. So there's my equation. Subtract 6 from both sides, subtraction property of equality, and then I'm going to go ahead and divide both sides by 3, which is a division property of equality, and I get 18 equals m. Now, there are some special segments in how they behave in isosceles triangles. So if I have a segment connecting the vertex of an isosceles triangle to the midpoint of the base, then this segment is a median because it's connected to the midpoint, vertex to midpoint. It's also an angle bisector because if angle A is congruent to angle C, and these are both 90, then you know that the angles formed at the vertex, so in this case, angle ABJ has to be congruent with angle JBC. So it's also an angle bisector. It's also a perpendicular bisector because we said that we had the 90 degrees here. And how do I know that it's 90 degrees? Well, remember before when we talked about equidistant, if it is these two, B is equidistant from A and C, and J is equidistant from A and C. And we mentioned that is the property of a perpendicular bisector, which happens when you have an isosceles triangle and it goes through the vertex. And then last but not least, because it goes through the vertex and it is perpendicular, it is also an altitude, or the height of the triangle. So this one segment here is 4 different special segments. Same thing over here. That one segment is also 4 special segments. If the segment goes through one of the base angles, so here, angle X, if I did X, Y, Z, then you don't get that same thing because, first of all, XS is the median because S will be the midpoint. XT right here would be the angle bisector. And then XU would be the altitude. And I don't even have the perpendicular bisector showing, but it would start at this midpoint and go straight up and down and not go through the vertex. So those special properties of being all the same types of segments has to do with going through the vertex angle, not going through one of the base angles. The exception is equilateral triangles, because since all 3 angles are equal, that means all vertices are the same. They're all the vertex angle. They're all 60 degrees, or you could think they're all the base angle. Since they're the vertex angle, though, that means that the segment is not only a median, it's an angle bisector, it's a perpendicular bisector, and an altitude. Now, the midsegment, I just want to mention briefly, will never be the same as the median, the angle bisector, or altitude because it doesn't have any of the endpoints on a vertex. The segments I just mentioned outside of the midsegment always have an endpoint on the vertex. So let's look at your last example, and we're going to classify the segment in each of the triangles. Now, I know you have a table, so I've broken it down, and I'm doing one row of the table at a time. First of all, let's look at triangle ABC. I know the legs are A, B, and BC, which means those are congruent. Now, as you can see these marks here, this tells me that BD is congruent to DC. That tells me that D is a midpoint. If D is the midpoint and I'm going from the vertex to the midpoint, that's the definition of a median. In triangle EFG, you can already see I have the answer. It's an altitude. Why is it an altitude? Well, first of all, here's the segment I'm looking at, EH, and I know that I see this 90-degree angle here and the vertex. So I know that if it's perpendicular and it goes through the vertex, then, and notice the vertex E there on that segment, then it is an altitude. On 3C, this is the 3rd row in your table, I have triangle IJK. So my legs are IK and KJ. This is definitely not the midpoint that segment's going through, but I can see that it bisects the angle here. So it is, since angle KIL is congruent to angle LIJ, this is an angle bisector. Then we have this one here, which is basically, you can see there's my segment, and I see that it's perpendicular. It is going through the midpoint, and so that tells me that it's perpendicular, and I also know the segments are congruent, so that means it's a perpendicular bisector. Remember, the bisectors cut things in half. Now we have triangle STU, and the legs are ST and TU, so those two are congruent. Here's the segment I have. So one thing you can see from the drawing is that these two pieces are congruent. So this is the midpoint V. So if that's the midpoint, that means that this yellow line, this segment TV, is the median. But since this is isosceles and these are congruent, see how I have congruent angles here? This tells me that, and that means there's just a perpendicular here. This is a 90-degree angle. So that tells me that it's also the altitude because it goes through the vertex and forms 90 degrees. And since it's perpendicular and it bisects the segment, it's a perpendicular bisector. If these angles are congruent, then that means that it has to bisect angle STU. So it's also an angle bisector. So for this table, you need to list median, altitude, perpendicular bisector, and angle bisector. Last but not least, I have triangle XWY, and my legs are XW and XY, and we have a segment ZQ. From the drawing, you can see that the line is parallel to the base here. Additionally, I can see that it cuts through the segments on each side, and so it goes through the two midpoints. That is the definition of a midsegment. So, on reflection, can the base angles of an isosceles triangle ever be obtuse? Now remember, you always have two base angles. Does it make sense that you could have two base angles more than 90 degrees? So justify your answer using a complete sentence in your notes. And for my pre-AP kiddos, I would like you to describe the orthocenter, the circumcenter, and the centroid for an isosceles triangle, and also for an equilateral triangle. You can just write that in your journal.